But as we talked about last time, you are here is not enough to navigate around in the world. If you want to go someplace else, like to the Stata cafeteria, you need to know other things, not just where you are. You need to know your heading direction, your current heading direction, okay? And so how was that coded? Well, it turns out that in addition to place cells in the hippocampus, in the structures surrounding the hippocampus, there's another kind of cell called a head direction cell. Okay, so these have been studied in rodents, and so these are cells that respond selectively when the rodent is facing different directions. He doesn't actually need to be locomoting in that direction, he just needs to be facing in that direction. Okay? And so here's a sort of schematic. Here's this rodent facing in 3 different directions, and here is a kind of hypothetical head direction cell that responds selectively to a given heading direction. Okay, you got that? And here's some real data of a head direction cell plotted of the 360 degrees as the rodent turns around and faces different directions. This heading direction cell fires most in that one orientation. So now we have the you are here with the place cells, and we have heading direction cells telling you what way you're oriented. Okay, those are 2 kinds of navigation-related cells. But the coolest navigation-related cells are known as grid cells, and they live in entorhinal cortex. I don't care about the details, but just to orient you, this is a slice through the brain like this. This thing is the hippocampus on both sides, and right underneath it, a region that sends inputs and outputs to the hippocampus and receives inputs from the hippocampus called entorhinal cortex. A little bit of cortex right next to the hippocampus is the main location where you find grid cells. Okay, so what's a grid cell? Let's look at the mapping of a grid cell. Okay, so here's another rodent going around in a box, and a dot is being formed whenever the neuron that's being recorded from makes an action potential. And so you got to watch for a while to see this. This is why these were only discovered in 2008, I think, something like that, maybe 2004. For a long time, people only knew about place cells, and they didn't really get what was going on here. You need to put a rodent in a somewhat bigger environment to detect the pattern, but does everybody see the pattern that's forming here? Like, whoa. Okay, that's a grid. It's formed an even grid, and if you put them in a larger environment, that pattern would repeat with the same exact regularity. Furthermore, it's a very particular kind of grid. It's a hexagonal grid. It's not X and Y coordinates, it's hexagonal. Okay, there's a whole lot of math about why it should be hexagonal, which frankly I don't understand, but apparently there are good computational reasons to go with a hexagonal grid rather than a Cartesian grid. So these cells, discovered by the Mosers in Norway, for which they got the Nobel Prize a few years ago, just blew everybody's mind, right? And so there's lots and lots of work on this right now. It's a super hot area. Nobody knows exactly what they do, but the gist is this is the kind of system you'd want if you wanted to keep track of how far you were going when you were walking around. It's like this ruler in your head that ticks off every time you go through a new little sub-place field within that broader grid field, right? And so the thought is that it's involved in measuring distances. It's like a ruler in your head. And it's very complicated. There's bunches of different grid cells that operate at different spatial scales and different subregions of entorhinal cortex. But the interesting thing is the grid cells that are in a given region of entorhinal cortex are all aligned with the same hexagonal direction. So if this is the receptive field or the place field of one grid cell, then right near it will be other grid cells that will have different subblobs that won't be right on top of these blobs, but the axes of the hexagonal grid will be aligned. And further, those axes will probably be aligned to something in this room. Like right now, you have grid cells in your head that are probably respecting this axis right here because it's the dominant thing that you're in. Okay. Okay, so here's a couple of grid cells mapped out in the same way, and this is just showing you in color the actually mapped out field, and the X's show you where the perfect hexagonal grid would be. Okay, so I think I just said all of this. One function that grid cells are thought to be important for is something called dead reckoning, which we humans don't do in much in these days in urban environments, because we use vision to kind of update where we are. But if you're a rodent walking around in the dark and you don't have external cues to keep reminding you where you are, you have to keep track of, you have to do a lot of calculus. You know, what is my velocity and my direction? You have to integrate as you change velocity and change your direction. And that's called dead reckoning or path integration, keeping track of how far you went in each direction and integrating the whole thing to come up with your current position. And so grid cells are thought to be part of the system that you use to tick off position as you go around in different velocities. Okay? Okay, I said all that. Okay, so now we have place cells in the hippocampus, right, that fire only when you're in one place. We have head direction cells in another, they're sort of all over the place, but mostly in the subiculum, which is right next to the hippocampus, that fire when you're oriented in a given direction, not when you're oriented in another direction. And grid cells that fire in this complicated set of multiple different locations in your world arranged in a hexagonal grid. Pretty amazing, isn't it? Okay, but there's one more kind of cell, and that's known as a border cell. So here are the place fields of a border cell. This rodent was placed into these different rectangles. There's probably 3 different cells here. And again, what the color shows is the rodent is just kind of migrating around. There's like mealy open bits because that means the rodent never went there, right? So of all the places in this rectangle where the rodent went, if he ever went there, we have a tally of how much the neuron fired when the rodent was there, okay? And look at how the place field of this border cell is oriented around this border of the box that the rodent is moving around in. This one is also oriented around the border of the box, and so is that one, okay? So you can see why these things might be useful. When you're navigating, you need to know where you can go and where you can't go. And if you're right near a border, like I'm walking along here, you know, some part of my brain needs to know that I can't like turn and go this way, right? So it's a navigational barrier, and there's cells that seem to represent your position with respect to those navigational barriers. All right? Okay. Okay, also, to do that, to set up these cells, you need to have a representation of the shape of space around you, a theme I keep coming back to because I think it's cool. And it comes up again and again. Remember, this is what the PPA cares about, the shape of space around you. And clearly, some kind of representation like that would be useful in setting up cells like this. Again, you need to know navigational barriers, where the walls are, okay?